as I said, in the last week, is considered by 4 bit of the binary number. Okay. So lastly, we stop at the half adder, all right, at the half adder, and also full adder. So we can add those numbers. We can add those numbers in the binary digit, okay, using adder. Okay, so today we're going to look further on the application of the logic gates. Okay. So the another application is the decoder. All right. So what's the function of decoder? So decodes mean it's inverse of the encoder. All right. It inverse of the encoder where you need to decode. All right. So let's say you have multiple bits. Let's say 101 1011, something like that, and then you want to decode that to a smaller bit. All right. So that's the function of decoder. All right. Let's say you want to decode it to 11, and then another one to 10, and another one to 1011. Okay. So that's the function of the decoder. All right. So why is that important? Okay, because it is used mostly in the computer design. All right, so let's say we look at the figure. Okay, figure 07. So shows the decoders for 9. Okay, 9 is a 1001 in the binary, and 5 using inverters and gates. Okay, so over here, okay, so we have, okay, let's say the output of the AND gate will be 1. Okay, will be 1 only if the input is binary. So meaning that, so whenever the input of the binary is 1, 0, 0, 1, that is 9, then the gate will function, right? The decoder will function, meaning that, let's say you want to, okay, you press 9 on your keyboard, okay, and then only this gate will function. It will instruct the decoder to output also 9, okay, to instruct at the output also 9 on the, let's say for example, on the printer, okay, or on your LCD screen. Okay, so that's the function. Okay, look for the B. So we have, let's say for the binary, so we have, let's say, okay, I'm going to write on this. Okay, so here on the top, because we have the least significant bit, so we have, so it should be starting from here. So we take 1 from here and goes to left. Okay, so it should be 1, 0, 0, and 1. Okay. So how about, let's say, you look at this. All right, let's say, so this should be, let's say all of that is 1. Okay, you have all 1 signal. Okay, and then this will be converted to 0 after this, to 0 and 0. Okay, and then this should be 1 and also 1. So when you multiply, right, when you multiply all of that, would it be 1? It should be 1 or 0. So what's your answer?
1.
1? Who said that? Who just said 1? Who said 1? Okay, raise your hand if you said it is 1. Okay, I assume I input it as 1, 1, 1, 1. Okay, so only 2 persons said 1. And how about 0? Who said it is 0? Okay, 5 persons said it is 0.
Tak tahu doktor.
Tak tahu.
Tak tahu.
Now we're going to learn. All right. So, okay. So should it be 1 or 0? Depends on the input. Okay. Now, I just said the input is 1, 1, 1, 1. All right. So when it goes after, okay, when it goes after this, right, should be at the input of the AND gate. So this should be 1, right, and this should be 0, and this should be 0, and this should be 1. So 1 multiplied by 0, multiplied by 0, and multiplied by 1. So you get 0 or 1? You get 0.
0.
Yes, you get 0. So as the function of the decoder will only give you 1 only if the input, this input is 1001, okay, or 9. Okay, so I hope you're clear with the function. All right, so now we have this. This is 9. Okay, so it will give it 0 at the output or 1. Of course, it should give you 1 because when 1 goes to here, it should be 1, and 0 to here, it should be 1, and here also 1. So all of that are 1s. So of course, we will have the output as 1. All right. Okay, similar to B. All right, so it should be no problem because here is only, all right, so here it is 5. Okay, here it is 5. Okay, what else that you can think of? What else that you can think of? What number? You can also put 1, 1, 1, and 1. So it's not a problem. Okay. And it can also be 0, 0, 0, and 1. So it's not a problem. So there are many numbers can be used for the decoders. All right. So as long as you put the configuration of the logic gates with the correct connection. Okay. So here, let's say you have this one, right? So we 1, 0, 1, 0. So here is the most significant bit. So this will be 1, 1, 1, 1, of course. This output 5. So you will get 1 over here. All right. Okay, so that's the function of the decoder. So you want to actually,
Doktor,
yes?
for the decoder, how can we know about the input and the logic gate that yang kena letak?
Okay, it depends on the actually input that you want. Let's say, what is your input? If you want to, let's say, the input number 4, all right? For example, I give 4. So how should you configure the decoder so that you have the AND gate and also the inverter. All right, so you configure it so the output will be 1. So how do you want to get it for?
0100.
Okay, so let's say, yes, okay, look at 4. All right, so it should be, you said 0100. All right, so okay, that's the input. Okay, so it should start from 0, 0, 1, 0. Okay, so what you need to do is to get all of this 0 to be 1 to get output 1, right? So you should put the inverter over there and inverter over there and also there. Okay, so this one, there will be no inverter. So of course the output will be 1. Okay, you get it?
Yes, doctor.
Okay, so basically you look at the input 0. So where at the input 0, you put the inverter over there. So that will be converted to 1. So you will get the result of the output will be 1. Okay, so we move on the flip-flop. So why we use flip-flop? So flip-flop is used for storing the data. Okay, and specifically the D flip-flop, okay, is widely used to latch data. Okay, so we have DFF. Okay, D flip-flop grabs data at the input as the clock is activated. Okay, so when this clock is activated, then this D flip-flop grabs the data at the input. Okay, and then it holds the data as long as the power is on. Okay, so this is basically the circuit diagram of the D flip-flop. Okay, so we have the NAND gate. Okay, we have the NAND gate and also we have an inverter at the bottom there. Okay, we look at the input of it. All right, so the circuit diagram is also to the block diagram as in B, and we have the truth table. Okay, so Q is the output. All right, and this Q is the inverse of that Q. Okay, so let's say this Q is 1, then this will be 0. If this Q is 1, then this one will be 0. Okay, so we look at the function of it. Okay, if if there is no clock, okay, if there is no clock, of course this won't function, so it won't change anything. Okay, it won't change anything at the Q. All right, and then okay, now the clock is functioning. Okay, so we have D. Okay, now D is 0. Okay, now D is 0, and then when the clock is functioning, then we have 1 and 1. All right, so here when it is 0 and it will be 1. Okay, and then over here we need to look at the signal that is output over here. All right, so over here, so let's say D is 0, so this will be 1 and then this will be 0. Okay, so what would be the input of that? Okay, so it could be 1 or 0. All right, so we look further. So let's say either of that, either this is 0 or that is 1. Okay, if it is 1, if this is 1 and 1 over here, so this one is 1. Okay, what should it be over here? Okay, of course you look over here, that will be 0, and let's say this is 0 or 1. Okay, so whenever 1 and 1, it will be 0 over here, and when 1 is and 0, it will be 1. Okay, so that's basically the input and output. So when this is 0 and 0, of course it will be 1, and when 1 and 0, it will be, okay, when 0 and 0, it will be 1, and when 0 and 1, it will also be 1. Okay, so you get it. So it is always 1 at the bottom here, because it doesn't matter when 0 multiply with 0, so you inverse that, you get 1, right? When 0 times 1, it will be 0, and also you get 1. So the input over here, will be always 1, okay? And then, so over here, you look back, so we have 1 and 1, so it will be 0. Okay, so it is, okay, so you get 0. The input of D is 0. Of course, when you will inverse this, you will get 1. Okay, so you can try by yourself. So you can try change that. So this would be 1. Okay, so this would be 1, and this would be 1. So here will be 0, and then clock is 1 and also 1. So at the output, it will be 1. Okay, and then here 1, 1, 1, and then you get 0. Okay, and then over here is a little bit tricky, so you need to ensure that you get the correct one. So you need to mention either is 0 or 1, and then give both inputs, and then you insert back to here, and then to check whether you get a constant value over here. So either it's 0 or 1, you still always get 1 over here. So it will always be 1 over here. So of course it will be 0. All right, so you get it. So here is, as it is 0, so it doesn't matter whether it's 1 or 0, you still get 1 over there. So that's why you get Q as 1. Okay. All right, so we're going to learn more on the terminology. Okay, so we have a bit. Okay, a bit is a binary digit. Okay, or a single binary digit. So it is a bit. It is a 0 or 1. And then we have nibble. As I just said, nibble is 4 bits. Okay, so let's say we can have either 1, 1, 1, 1. Okay, that is a nibble. 1, 0, 1, 0, that is a nibble. And 0, 0, 0, 0, that is a nibble. So a nibble is 4 bits. And we have byte. So this is the term that we use commonly. Let's say megabyte. Okay, so it is different with megabit. Okay, you need to remember that byte is much more higher than bit. Bit is just a single. Okay, compared to 4 byte and 4 bit. Of course, 4 bit is equals to nibble. And then 4 byte is actually, you have how many bits? So you multiply with 8. Alright? So it is 32 bit. 4 byte equals to 32 bits. Alright, so as just said, a byte is defined as 8 bits. And then we have the term of word. So word is 16 bits. So how equivalent word to nibble? Okay, so one word is equal to 4 nibble. Alright, or it can be equivalent to 2 bytes. Okay, so you can interchange all of those terms together. All right, so Now we have kilobyte. Okay, what is kilobyte? So kilo is 2 to the 10 bytes. Okay, so kilo is 2 to the 10 bytes, which is 1024 byte. Okay, that is a kilobyte. Okay, so the abbreviation K. So K byte is usually represent kilobyte. A megabyte, so it will in the multiplication of uh, 10 and 10. All right, so kilobyte is 2 to the 10, megabyte is 2 to 20. Okay, so megabyte is a little over 1 million bytes. Okay, so exactly at 1048576 bytes. A gigabyte is, okay, so you increase 10 more, so kilobyte, megabyte, gigabyte, so 2 to the 30 bytes, so it's over 1 billion. Okay, and a terabyte, so you increase more, so you have 2 to the 40 bytes. Okay, all right, so that's the definition. Okay, so inside the computer we also have RAM. Okay, so what is RAM? RAM is a random access memory. Sometimes it is called as read or write memory. And we also use RAM to temporarily store the program while running. Okay, so the data is lost when the computer is turned off. Okay, so the RAM is usually a card slot inside a computer where you can add it. Let's say right now they are using the PCI Express connectivity. Okay, so you just slot in, so you can add this RAM actually to your computer. Let's say your RAM now is 8 gigabyte. Okay, is 8 gigabyte, and then you can increase. Let's say 16 gigabyte, 32 gigabyte, right, and 64 gigabyte. Okay, so you can increase your RAM. Okay, so the usage is to temporarily store the program. Okay, so if you have multiple program running and you have small RAM, so of course your computer will slow down because you fully utilize the RAM. So to solve that problem, you need to increase the RAM. Okay, you need to increase the RAM to cater for all of the running programs. Okay, and also if you want to reduce the usage of RAM, you need to close some applications. So your RAM is now free again to be used by other process. Okay, and we also have ROM. So ROM is the read-only memory. Okay, so the ROM is the one that comes together with your microprocessor. Okay, so it comes together with your microprocessor because it is used to store the information that is essential to the operation of the computer. Okay, so the ROM is permanent and cannot be changed by the user, and it is not lost when the computer is turned off. Okay, so because when you turn on your computer, it needs to be this ROM contains set of instruction for the to instruct microprocessor what to be done. Okay, if this ROM is not available, of course, even though you have the microprocessor there, your computer still cannot be run. Okay, so because let's say, okay, once the user switch on the power button, can instruct the microprocessor, okay, to turn on your LCD, to turn on your monitor, all right, and then to make the keyboard functioning, okay, and to make the mouse functioning. Okay, so that is the function of the ROM. Okay, so ROM is called the non-volatile memory. Okay, so that's the difference between RAM and ROM. Okay, so inside the computer, so the internal workings of every computer can be broken down into three parts. Okay, so first we have the CPU. The CPU is the central processing unit, okay, where everything is controlled over here. And then next we have the memory. So the memory contains RAM and ROM, okay. And last we have the input and output devices that is connected to the computer, right? Such as the monitor, printer, right? The keyboard, mouse, okay? The what else? The USB drive, okay? So that's all the peripherals that is connected to the computer. Okay, so to have the communication between the CPU and also with the memory and the peripherals, so we need to have a highway. So that highway is called a bus, right? So we have over here, let's say, you look over there, we have the address bus and also the data bus. Okay, so the CPU function is to execute the information stored in the memory. Okay, so the function uh, inside the memory needs to be executed by the CPU. Okay, so that is the function of the CPU. And then the input output devices, for example, as keyboard and monitor, provide a means of communicating with the CPU. All right. So whatever it is, you want to, of course, you need to have the user input. User input to the computer and then it works. Okay. If you don't do anything to your computer, of course, the computer will just stay there without doing anything. So the CPU is connected to the memory and I/O through a group of wires called a bus. All right. So it allows the signals to carry information from place to place. This is what we call as highway. Okay. So in every computer, there are three types of buses where we have the address bus, the data bus, and lastly, the control bus. Okay, so for a device, okay, whether it is a memory or input or output to be recognized by the CPU, it must be assigned an address. Okay, so it's like uh, your house, all right? So like a CPU. So you mentioned that like a CPU is like UPM, all right? It's like UPM campus. And then let's say your home, you should have the address at your home. Let's say your house is one is in Putrajaya and the other one at the Cyberjaya. Okay, so it must have the address, the specific address of that. Okay, so the computer needs to function at that. So you assume that the UPM campus is like the CPU, and then your house at Putrajaya is like the memory, and the input output device is like your house at Cyberjaya. Okay, so of course you cannot have the same address. Okay, you cannot have the same address because when you have the same address, there will be conflict. Okay, so inside the computer, so the similar concept should also be used. So no two devices can have the same address. Okay, the address assigned to a given device must be unique. Okay, so the CPU puts the address in binary on the address bus, and the decoding circuitry finds the device. So the decoding circuitry is the decoder that I just explained before. Okay, so that's the function of the decoder. Okay, then the CPU uses the data bus either to get data from that device or to send data to it, right? So let's say you input the data, all right? So you input the data from your keyboard, okay, from your keyboard, and then of course you want to get the output. So the output could be monitor, right? So a monitor or a printer. Okay, let's say the input device is a keyboard, and mouse is also an input device, and the output device, the example is like monitor and printer. Okay, so when you input, let's say you press number 7 on your keyboard, and then you must want to be displayed on the LCD as 7 as well. So you send this information to the CPU through the data bus, and then the CPU send back to the monitor also through the data bus. Okay, so that is the function of the data bus. Okay, and then the control bus, okay, and the control bus provide the device read or write signal. Okay, this is to indicate if the CPU is asking for information or sending information. Okay, so you have the data, but that need to be controlled, whether it is to be written or to be read just or write. Okay, so that's the function of the control bus. Okay, so okay, you have a more complex block diagram. So you have, okay, so the CPU can read or write. So we have the address bus on the top here, and then the data bus at the bottom here. And then we have the control buses as well. Okay, we have the control buses as well. Okay, for example, so all of the address bus must be connected, okay, from CPU to all of the devices. Okay, but for the data bus, so it depends whether you want to be input or output. Okay, you want to be input or output. So we look over here. So we have, let's say, the RAM. Of course, the RAM will be both direction, because sometimes we need to store, and then sometimes we need to release the information. Okay, so that's why we have both arrows for RAM. And ROM is going out only to the CPU, because the ROM, as I just said before, is store the information to instruct the CPU to do anything. Okay, either to start the computer, to run the operating system, right, and so on. So that's the ROM, function of ROM. And for the printer, of course, it will be, because printer is the output device, so the CPU needs to send the information to the printer. Okay, and this drive is similar to RAM function. Okay, so that's why it will be on both direction. Okay, and the monitor, of course, it will be just output. So want to display the information, so it just be from the CPU, okay, to the monitor. And then for the keyboard, so because the keyboard is the input device, so what you need to do is just press the key on the keyboard and then instruct the CPU to do anything. So the direction is just from keyboard to the CPU. And then look at the control buses. So the control buses is also like the address bus. So it is from CPU to all of the devices. Okay. All right. Okay, so the data buses carry information in or out of a CPU. And then the more data buses available, the better the CPU. Okay, so because it's like a highway, if you have more lanes, so it is better, right? So because you can have more cars, okay, you can have more cars traveling at a higher speed. All right, if you just have one lane and the car in the front is slow, so you you have the problem to overtake that car. Okay, so you cannot go faster than that. But if you have more lanes, of course you can easily take over the car. All right, so because you have the dedicated lane for yourself. Okay, so if the data buses is more, then the information can be sent much faster. Okay, but the thing is, it is more expensive. Okay, so it is more expensive. So that is why you have the more processing power. Okay, multiple core of the CPU. That's why you have more expensive CPU unit. Okay, because it contains more data buses. All right, so it's like a highway. So rather than you construct, if the government just a single lane road, of course the cost is much less compared to you need to construct a highway. All right, so that's the difference between cheaper CPU and higher end CPU. Okay, and the data buses are bidirectional, meaning that you can use the lane, right? You can use the lane for both direction, whether it's going from the CPU to the device or to the device from the device to the CPU. Okay, so the average bus size is between 8 and 64. All right, so that's the size of bus. Okay, so the computer processing power is related to the bus size. Okay, an 8-bit bus can send out 1 byte at a time. Okay, a 16-bit bus can send out 2 bytes at a time. Okay, you just remember that 1 byte is equals to 8 bit. All right, so that is the equivalent of that. 2 bytes is equivalent to 16 bit. Okay, so the address bus is used to identify devices and memory connected to the CPU. Okay, so this is the function of the address bus. Before that, so we have the data bus. So the data, you want to send the data. Okay, so for the address is to identify the device. Okay. Okay, so if we have more address bits available, of course, we can have larger number of device that can be addressed. All right. Okay, so it's like if you have more address, let's say you can use more peripherals or more devices. Let's say input, you can input more memories, you can have more input device. Let's say you can have more monitors, right? You can have multiple printers, okay? Because whenever you have bigger address bus, you can connect your CPU to many other devices. Okay, so that's the function of the address bus. Okay, so you notice that the comparison between address bus and the data bus. The data is just between the device and the computer. All right, but for the address, it depends on the number of the devices. Okay, it's not specific on the data transfer between CPU and the device. Okay, so the number of CPU address bits determine the number of locations with which it can communicate. Okay, so it is always equals to 2x to the power of x, where x is the number of address lines. Okay, and regardless the size of the data bus. Okay, so I just said it determines based on the number of location which it can communicate. Okay, so it's like I just said, we have UPM as the CPU, and there's you have a house at Cyberjaya and Putrajaya. So now if we have add more address bus, of course you can add more location of the house. Let's say now I want to connect to your friend's house at Puchong now, and then go to Johor Bahru, and then go to Kuala Terengganu, go to Kota Baru, alright, go to Alustar, and so on. Alright, so when you have more address bus available, so you can connect to multiple devices. And the address bus is not like the data bus. It is just the unidirectional. Okay, because CPU will find those location. It will find those device. It is not the device finds the CPU. Okay, it is the CPU that finds the device. Okay, that's why it is only unidirectional. Okay, we need to define the relationship of the CPU to the RAM and ROM. Okay, so for the CPU to process information, the data must be stored in RAM or ROM. Okay, and then the CPU cannot get the information from disk directly because the disk is too slow. Okay, so because last time the disk is designed based on what we call as the, it's like the what we call that, it's based on the silicon. Okay, it's based on the silicon, so it is much slower compared to the RAM and ROM, because the running speed of the disk is, let's say last time we have about 3000 rotation per minute, so it depends on the rotation of the disk. Okay, so the disk made of the silicon, all right, so it is small, so it depends on the rotation, so it needs, you need to increase the speed of rotation so the information can be read faster. Okay, but today we have much more better technology, so the disk is already made in terms of solid state, so it is like a memory right now. So the disk now is like a memory, because nowadays the memory can be made much cheaper, so you can have the disk at a cheaper price right now, and at the same time you can have the information faster. Okay, so that's why in the previous days the CPU is connected to the RAM and ROM to obtain the stored memory. Okay, so that's why the RAM and ROM are often called as the primary memory, and the disks are called as the secondary memory.
Doctor,
Yes.
Kalau if the disk is solid state, so it can be primary memory.
Um, Still cannot be. Of course, the RAM technology is actually much faster nowadays. Alright. So the RAM technology is much ahead uh, steps compared to the disk technology. So it is actually much faster nowadays to store the information inside the RAM. Okay, so it can use the solid state, but it's not designed. It's still not designed to be used as RAM or ROM. Okay, it is not used for RAM and ROM. So because it's actually, so this is, let's say, the speed of the ROM in the last few years, and then this is the speed of the disk drive on the last few years. And then when the time moves, so this actually move at a steady rate, but this one actually move at the higher rate. Okay, but it's still the speed of the disk much slower than the RAM. Okay, so that's why we still not use the RAM and CPU based on the solid state drive. Okay, but actually you can create if inside the operating system you have the function as the virtual memory. Okay, so it's like you can use partially based on your disk. Okay, you can use, if you want to increase that, if you have the solid state drive in your computer, you can use that function, the virtual memory inside the operating system, like in the Windows, you can use that to increase your RAM capacity. Okay, so you need to know that usually the RAM and ROM is only used to instruct. Okay, to instruct, let's say you want to open the application to run the application, but for the data transfer we still use the disk drive. Okay, so that's the difference function of how memory works and how the disk drive works. So the disk drive just to store and write in the information, store and write. But for the RAM is for running the application. Okay, so that's the difference. So that's the answer for your question. So it's still not, because we still need to differentiate. Okay, we still need to differentiate between the disk and also RAM. But if you want to make it cheap to use solid state drive as part of your memory, it can be done. Of course, it can be done. All right, because the solid state memory nowadays is actually, the speed is much faster compared to the previously the disk drive based on the, what we call the spinning rotation. Okay, based on the spinning drive. All right. Okay, so we continue with the, okay, with the inside the CPU. So we have a program stored in memory provides an instruction to the CPU to perform an action. Okay, let's say we want to add the payroll numbers or controlling a robot. Okay, so we have, okay, the function of the CPU is to fetch these instructions from memory and then execute them. All right. Okay, so we have, let's say, figure 019. So we have the internal block diagram of the CPU. Okay, so where we have the address bus over here, so which is the program counter. Okay, and then the control bus. Okay, in the control bus, and then we have the data bus. All right, so the data bus is connected to the internal bus. So this is inside the CPU. So we have flags and ALU, right? So for the function of CPU is to fetch the instruction from memory and then do the execution. So it needs to take the information from the memory and then execute. Okay, so it is like a middleman. Okay, let's say the farmer produce the crops, okay, and then the middleman take the crops and then distribute to the other sellers, for example. So that's the function of the CPU. Okay. Okay, to perform the action of fetch, fetch is take the information and then execute. So all CPUs are equipped with resources such as registers. Okay. So registers to store the information temporarily. Okay, so like this figure. Okay, so we're going to describe those actually this diagram. Okay, this is a diagram inside the CPU. Okay, so this diagram inside the CPU. So we have the registers, okay, which store the information temporarily. So it can be 8, 16, 32, or 64 bit. So it depends on the CPU. And then we have ALU. So ALU is the arithmetic or logic unit. Okay. So ALU contains the logic gates. All right. So it contains the logic gate where you need to perform addition, subtraction, all the mathematical computation need to be done at the ALU. Right, so we have a function, okay, add, subtract, multiply, and divide. Okay, so and also logic functions such as AND or AND not. All right, and we also have the program counter, okay, to point the address of the next instruction to be executed. Okay, so we have the program counters over here. So the program counters, okay, is connected to the address bus. So you remember that this address bus will be connected to the devices. All right, that is connected to the devices. So in the IBM PC, a register called IP, okay, or instruction pointer, okay. And then lastly, we have the instruction decoder to interpret the instruction fetched into the CPU. Okay, so this is the instruction decoder. Okay, so it's over here. So mean that we need to take the information from this ALU and so on, it to be sent to the devices. For the program counter over here is to be connected to the device, and then instruction is to send the instruction to the devices. And then for the registers, it is connected to the data storage. Okay, so that's the difference between those three functions inside the CPU. Okay, so of course the main thing is the ALU without computation. So that's why it is the name of the computer. So you need to compute. So the computation is done at the ALU. Okay, so that's the main function inside the microprocessor. A step-by-step analysis of CPU processes to add three numbers with steps and code shown. All right, for example, over here, so we have CPU has registers of A, B, C, and D. Okay, so we have an 8-bit data bus and 16-bit address bus. Okay, and then the CPU can access memory address from 0000 to FFFFH. Okay, so we have a total of how many locations? 10000H locations. Okay, so that's the total memory address that the CPU can access. Okay, so for example, we want to move. Okay, now you are doing the action to add 3 numbers. Okay, you want to add 3 numbers, and then you want to move that to register A. Okay, so move the value 21H into register A. Okay, so we have the code. Okay, one code is B0H. Okay, and then the data is 21H. Okay, so the data is 21H because this is the value. Okay, 21H. Okay, and then we add more value. Okay, say 42H. So we add value 42H to register A with different code. All right, so with different code, and then we have 42H right now. Okay, and then we add more 12H. Okay, so you need to, okay, so the difference between that, so this code is like the instruction. Okay, so it is like the instruction. So moving. Okay, so for move, so the code is B0H, and addition, the code is 04H. Okay, so this is complement by the data. Okay, so the data is the value that is used to move. So move, this move is instruct by the CPU by this code. Okay, add is instruct to the CPU by this value. Okay, so this is for add. But this data, this value, this value is the data value. Okay, so that's the difference between the action and then the value of that. Okay. All right, so this is more function of that. Okay. So every action, we have different code inside the memory. Okay, this is the one that is put inside the ROM actually. So this is what is stored inside ROM. So if the program to perform the action listing above is stored in memory locations starting at 1400H, and then the following would represent the contents for each memory address location. So you look at the code. Okay, so we have, let's say, memory address 1400. So is to move, B0 is to move, and 1401, 21 value to be moved. Okay, so that's the value, and then 04. So we use the memory. Okay, so 1402 is the code for adding. So it's by consequence, okay? So first you move, and then move have certain value, add have certain value, and add again have certain value. So you have how many steps there? So you have 1, 2, 3, 4, 5, 6, 7. So you have 7 steps. Okay. So first to move, and then value to be moved. So and then add, and then a value to be added, and then code to move. Code to add, right? And then value to be added, and then lastly code for how. Okay, so the program stop. So you have 7 steps. So it use 7 locations in the memory address. Okay. So once it is finished, okay, once it is finished, so the memory can be stored or released. So if erased, all of the information will be erased. But let's say if you want to choose to store only the final value, so the memory address, okay, at 05 will remain, okay, and then other location in the memory address will be erased. Okay. Give me a few seconds. Got some problem with the slides. Hold on. Give me a few seconds, few minutes. Okay, can you hear me?
Can Doctor?
Okay, all right. Okay, let's continue. Okay, so we have this. All right. So let's say a CPU program counter can have a value between 000 and FFFH. All right. So the program counter must be set to the address of first execution of the code to be introduced at 1400H. All right. So the CPU puts the address, okay, 1400 hash on the address bus and then sends it out. Okay, and then the memory finds the location. Okay, now so the CPU send the information to the memory. Okay, and then the memory need to find the location inside it. All right, which of the, let's say, which of the cluster is still free to be used inside the memory. So you need to find. Okay, need to find, and okay, now it uh it found the location. Okay, while waiting for the CPU activates the read signal. Okay, indicating that it wants the byte at 1400. Okay, and then the content, now the value. Okay, the content B0, okay, which is the move instruction. The move instruction, okay, now can be put on the memory. Okay, once the instruction can be put, and then the that content can be transferred, okay, from the CPU to the memory on the data bus. Okay. First, the address bus will function, and then next, the data bus will function. Okay, so you can differentiate between those two. Address to find the location, all right, instruction, find the location, and then the data is to do the action, all right, data is to do the action. Okay, so once it finds, and then the CPU send the information through the data bus. Okay, and then so the information now, okay, now it finds the information, all right, and then the memory can also send that information back, okay, to the CPU, okay, by using the data bus. Okay, now we want to move the value, right? So the CPU decodes the instruction B0, okay, with the help of its instruction decoder dictionary. Okay, so the function now is to bring the byte to the next memory location into CPU register A. Okay, now I need to bring the byte of the next memory location into the CPU register A. Okay, so now it use the instruction decoder. Okay, now the CPU uses the instruction decoder. So like this one on the figure here. Okay, this one. So it use the instruction decoder, right, to put that on the register. Okay, to put that on the register. All right, and then okay, and now the next instruction is to add more value. Okay, now the value has been moved. Okay, now to add more value, so from the memory location 1401H, the CPU fetches code 21H directly to register A. Okay, so it fetch the code 21H directly to register A. After completing the instruction, the program counter points to the address of the next instruction. Okay, now again, similar to initial process. So the address 1402, okay, is now sent out on the address bus, okay, to fetch the next instruction. Okay, so once it fetch on the address, of course, next is the data transfer. So we need to use the data bus. Okay, so after that, so CPU fetches the code 04H, all right, and then after decoding, the CPU knows it must add the byte at the next address, okay, to the contents of register. Okay, so after it brings the value 42H into the CPU, it provides the contents of register A along with this value to the ALU. Alright, so it brings back to the ALU to perform the addition. Okay, now the program counter, okay, so because the counter will keep increasing. So once one instruction is done, okay, the counter, okay, add one more number from 1402 to 1403, and then next 1404, okay, for the next instruction address. Okay, so it is like, so every function needs to be instructed, needs to go to the address bus. Okay, and then the address 1404H is put on the address bus, and then the code is fetched and executed. Okay, again, adding a value to register A. Okay, the program counter now updated, okay, to 1406H. Okay, so that's the process that is followed after fetch, decode, and executed. Okay, so the process first put and read on the address bus, and then next code is fetched, decoded, and executed. All right, and then the contents of address 1406 are fetched in and executed. Okay, the halt instruction tells the CPU to stop incrementing the program counter and asking for the next instruction. Okay, without halt, the CPU would continue updating the program counter and fetching instruction. All right, so that is the process on how you use the communication between the CPU and the memory. Okay, so to move one value, all right, to move one value, and then to add more value to the process. Okay, so it consists of function of address bus, and then also the data bus, and when decoding the information, it use the control bus. So all of those three buses are used when instruction is done. Okay, so are you clear with that? I will give more example later after uh, after we finish with the lecture later, to make you understand better on the concept of how the address bus is used. All right. Okay, so that's it for the introduction. All right, any questions so far?
No, doctor.
Okay. All right. Let me find out. Have a rest for a few minutes. I'm going to look for the notes, all right, for the next chapter. So we're going to continue for a few minutes. After that, we will continue the rest of the time on Thursday, right? Okay. I'm going to share you the next slides. You can download it on the WhatsApp group. Um, where is the okay? Okay, that's the next slide. So you can download on the WhatsApp group. Now we're going to learn on the what is the x86 microprocessor is. Okay, what is the x86, the microprocessor? Okay. So in this chapter, you will learn Intel family of microprocessor from 8085, okay, which is the first version of the Intel microprocessor, to the Pentium. All right. So in terms of bus size, okay, so you learn about the bus size, physical memory, and the special features. Okay, and then you need to explain the function of the EU. Is the execution unit, and the BIU, the bus interface unit. And then we're going to also describe about the pipelining and how it enables the CPU to work faster. And then list the registers of the 8086. So you know that the register is where the instruction is connected to the data buses. All right, so that's the function of register. And then code the simple move and add instruction. Okay, describe the effect of this instruction and their operand. Okay, so here, okay, the student should also be able to state the purpose of the code segment, data segment, stack segment, and extra segment. Okay, and then explain the difference between a logical address and a physical address. Describe the little Indian, little Endian, so it's not little Indian, it's the Endian storage convention of the x86 microprocessors, and state the purpose of the stack, and explain the function of push and pop instructions, and list the bits of the flag register and briefly state the purpose of each bit. Okay, so it's quite a long chapter. So you also need to demonstrate the effect of add instruction on the flag registers. This is the addressing modes on of the 8086 and recognize examples of each mode, and then know how to use flowcharts and pseudocode in the program development. Okay, so before we end today, so we're going to briefly talk about the brief history of the x86 family evolution from 8080, a microprocessor, or 8085 to the 8086. So in 1978, so I believe you guys have not been born yet, all right? So Intel Corporation introduced the 16-bit 8086 microprocessor, a major improvement over the previous generation of 8080 or 8085 series. So the 8086 capacity of 1 megabyte of memory exceeded, okay, the maximum capacity of 8085 or 80 processor with maximum of 60k bytes of memory. Okay, so you look at the difference. Okay, so 1 megabyte, okay, 1 megabyte is equivalent to 2 to the 20, okay, 2 to the 20 uh, byte of memory. Okay, and then 64 bits, 64k bits. So 1 kilobyte is equivalent to 2 to the 10. So 64 times 2 to the 10. Okay, now is up to 2 to the 20. Okay, so it is much more bigger memory. All right, so, and 8085 was an 8-bit system which could work on the only 8 bits of data at a time, right? And the data larger than 8 bits, right, had to be broken into 8-bit pieces to be processed by the CPU. Okay, so if the data is bigger than 8 bits, it must be broken first. So that is much slower process compared than when you have 8086, right? So it is designed as a pipeline processor, okay, as opposed to the non-pipeline. So the previous one, so we have the 8080 or 8085 using the non-pipeline technology. Okay, so meaning that over here the data does not have to be broken anymore as in the 8085. So all of information that exceeds 8 bit can be just sent without being broken. Okay. All right. So we look at the evolution of the Intel's microprocessor from 8008 to the 8088. Okay. So that's the product of the Intel. So 808 introduced in 1972 and up to 1979. Okay, the technology using PMOS in the 8008, okay, and use the NMOS, okay, from 8080 to 8088. All right. And then the number of pins used on 8008 is just 18, but For the 8080 to 8088, it's all use 40. All right. And then the number of transistors used is 3000 for 8008. And then for 8080 to 8088, okay, so you look at tremendously increase to the number of the transistors. So this is actually according to the Moore's law. So if you know that the Moore's law, so it is expected that the number of the transistor used for building the microprocessor, okay, increase double for every decade. All right, so it's double for every decade. Okay, so the number of instruction when we have more transistors, so the number of instruction increase from 60 to 133. Okay, so from 60 to 133 from uh, 1970 to 1978. Okay, and at 1979 it still use 133. So the only improvement from 8086 to 8080 processor is actually a very small improvement. Okay, as you can look here, it's nothing much change except for the internal data bus. Okay, sorry, for the external data bus. Okay, which is used a much smaller data bus compared to the 8086. So if you want to know more, you can find out the answer why 8086, why 88 is using much smaller data bus compared to the 8086. But the 8080 processor is produced later compared to 8086. So there must be a reason behind that. All right. So other than that, all of the features are similar to 8086 processor. Okay, and 8086 microprocessor has a 16-bit data bus internally and externally. All registers are 16 bits wide, and there is a 16-bit data bus to transfer the data in and out of the CPU. Okay. So when there was a resistance to a 16-bit external bus, as the peripherals were designed around the 8-bit processor. Okay, printed circuit board with a 16-bit data also cost more. All right. As a result, Intel came out. Okay, this is the reason. Okay, this is the reason why back to in the 1979, so the 8088 version is introduced. Okay, so because the 16-bit data costs more, but the technology, all of others are similar. So actually the 8088 processor can be produced much lesser. Okay, so it is much cheaper to buy the 8088 processor. So this processor has been picked up by IBM. So last time the IBM was the producer of the computer. It's like Dell, so it's like HP, it's like Acer. So IBM nowadays already known as sold is their PC business to the Lenovo. All right. So the IBM during that time used that microprocessor to design the PC. Okay, so 8080 based IBM PC was a great success. So because IBM and Microsoft made it an open system. Okay, the documentation and specification of the hardware and software of the PC were made public. Okay, so it make it possible for many vendors to clone the hardware, right, successfully, and spawn a major growth okay, in both hardware and software designs based on the IBM PC. Okay, so because it can it can be sold at the cheaper price. Okay, so the people can buy the PC. So that's why it is a successful microprocessor. Okay, during that time. So if the PC costs, let's say 300 or 400 USD, of course the people can buy it. All right. So it is possible for the further development of the technology itself. Okay. So similarly, it's like the mobile phone nowadays. So last time we only have the Samsung and also Apple, all right, as the producer of the mobile phone, okay, for the touch screen mobile phone. But nowadays we have more options. Let's say we have the Vivo, all right, we have Realme, we have Oppo, right? But that can be produced at cheaper price. So when they can be sold at cheaper price, so we have more possibilities for the advancement of the okay. So that is a good thing when the technology is getting cheaper and cheaper. All right, so later Intel introduced the 8286 in the 1982, which IBM picked up for the design of the PC80. All right, so it used the 16-bit internal and external data buses. All right, and then it has the 24 address lines for the 16 megabyte memory. So 16 megabyte is 2 to the 24, right? 2 to the 24 in terms of binary digit, and it is a virtual memory, right? So the 8286 can operate in two modes. Okay, the real modes, okay, a faster 8080 or 8086 with the same maximum of 1 megabyte of memory, or in the protected mode, which allows for 16 mega, okay, 16 mega of 16M of the memory. So I need to check this term again. So what does it mean by 16M memory? So it is capable of protecting the operating system and programs from accidental or deliberate destruction of the user. Okay, so there are two type of the mode operation for the 8286 microprocessor. Okay. All right. So this is what I just mentioned about the virtual memory. So virtual memory is a way of fooling the processor into thinking that it has access to an almost unlimited amount of memory by swapping the data between the storage and RAM. Okay. So that was one function on the 8286 microprocessor. So in 1985, Intel introduced 8386 or 8386DX. Okay, it is a 32-bit internally or externally with a 32-bit address bus. So it is double now the capacity of the address bus. Before that, for the 8286, it's just 16-bit address bus. Okay, and it is capable of handling memory of up to 4 gigabytes. Okay, up to 4 gigabytes, which is 2 to the 32 in terms of the binary digit. Okay, so or 2 to the 32 bit. Okay, so the virtual memory now increased to 64 terabytes. Okay, is 2 to the 46. Okay, and then later Intel introduced 386SX, which is internally identical but with the 16-bit external data bus and 24-bit address bus. Okay, so it is actually identical for the internal data, okay, for the internal address bus, but externally you make it smaller. All right, externally you make it smaller, so it just function with the 16-bit for the data bus, and then for the external data address bus it is just 24-bit. Okay, so when you are making a smaller highway, all right, when you're making smaller highway, let's say the lane is much narrow compared to some highway have a bigger lane. All right, some highway have a smaller have a tiny lane or a much compressed lane or a narrower lane. So of course the cost of construction of those will be much more less. All right, so that's why the 386SX system is much cheaper. Okay, since the general purpose processors could not handle mathematical calculation rapidly, Intel introduced numerical data processing chip. Okay, so the mathematical computation, which is the main function of the CPU, must be done rapidly because you want to call it 1 plus 1, 1 plus 2, and so on. That must be done quickly, so that because from there you can run multiple application and so on. If it is slow, then of course they will be lagging in terms of the user interface. All right, let's say you want to type Apple on the keyboard, and then later the Apple, the word A will arrive at the screen, at your screen, maybe 1 minute later. So that's not giving you any convenience in using the PC because the processing power is very small, very low. All right. So that's why the Intel introduced the math co-processor such as 8087, 8287, 8387. Okay. And then in 1986, Intel introduced 8486. So it enhanced the 8036 and math co-processor on a single chip. So now you have both chips, all right, both processor. One processor for the normal operation, and then another processor just for the mathematical computation. Okay. Plus, it puts the additional features such as the cache memory, right? So cache memory is a static RAM with a fast access time. Okay. So all programs written for the 8080 or 8086 will run on 286, 386, and 486 computer. All right. Okay, so that's it up to the 8086 processor from 8008 processor to 8086. Okay, so on Thursday, we will continue with the 8086 to the Pentium Pro processor. Okay, right. So that's it for today. Okay. So lastly, as usual, I'm going to take the attendance. So you all can turn on your camera right now. All right, so I'm going to count from 10. All right. So, okay, be ready. All right. So 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And smile, everyone. Okay. One more. Hold on. All right. One more. Okay. Thank you. All right. So I see you again on Thursday.
Okay, sir.
Okay,
Thank you.
doctor.
Okay.
Okay,
Welcome.
doctor.
Cool, doctor.
Thank
You
you.
doctor.
Thank you, doctor. You
Thank you,
doctor. You doctor.
You doctor.
you,
All right.
doctor.
So all the best for the rest of the day.
Okay, doctor. See you, doctor.
Ah,